Good afternoon. Today is the last day of this class, and we will learn about the modern defense techniques, including control flow integrity and others. Let's start with summarizing what we have learned first. And in week 1, we learned how to read assembly code and interpret this as generic languages as a somewhat understandable program, and then learning about how program works. So in other words, we learned about the basic reverse engineering in week 1. And in week 2, we learned about the basics of the buffer overflow vulnerability and how we can exploit that. And mostly we learned about how we can override control data such as save the BP or the return address to control the change the control flow of the program. And in week 3, basically, we learned how to write the assembly. So in week 1, we learned about how to read and interpret the assembly. So after week 3, we have a comprehensive analysis, understanding about the assembly code. And then basically, we learned about how we can write the useful programs using opcode. Basically, we wrote a shellcode that spawns a shell because after spawning a shell, you can run any kind of program, so you can do whatever you want. So after learning the shell, you can say you achieved arbitrary code execution because you can run arbitrary program. And then starting from week 4, we are introduced with some other defenses, and we learned about the DEP, data execution and prevention, which prevent shellcode injection and running, and ASLR, address space layer randomization, which randomizes address layout per each execution, like the example in the screen, and the stack cookie, which detects which acts as a canary for detecting the smashing the stack for the control data. And we also learned how we can avoid such defenses. And along with that, we learned about the useful command that was pawn checksec. And using this command, you can check the security mechanism application status of the program. So this one is a quite secure one, BNSH, which is an important program. We use it for attack, but the program itself is very secure. And it says it is applied with the full relo, so that you cannot overwrite your GOT at all. And then stack canary is found, you need to defend that and to attack the Buffer-Overflow vulnerability, and the NX is enabled, so the DEP is active, so you need to launch a return-oriented programming, and PIE is active, so it's a full ASLR, so you need to have some of the at least a sequential and also for the arbitrary leak for the to get the layout of the addresses, and then it is enabled with the D45 source 2. So even if you have a format string attack primitives, then you cannot use that as an arbitrary write because the %n is blocked. Yeah. And in week 5, we learned about the return-oriented programming, and even with the much restrictions that we cannot inject our shellcode, by using return-oriented programming, we can implement any kind of logic by connecting ROP gadgets. For example, these pops and return. So in 32-bit, we only cares about how many pops before return we have, because argument passing is done by the pushing and popping the stack. But in 64-bit, argument passing is done over specific registers. So the pop to the which register, so that is important. So pop RDI return is for setting the first argument. Pop RSI and something return is a second argument. RDX and return is setting the third argument, something like that. Yeah. And by chaining these kind of our ROP gadgets as a chain, we can write the Turing complete program. So it's ROP is a powerful code reuse attack to defend against the data execution prevention, and also for the ASLR for the non-PIE binaries. So mostly we can, if we can find all the gadgets in the code area, and if the binary is a non-PIE, then that's completely without ASLR. So this is one of the ASLR breaking technique. And in doing ROP, we also practice that we can build an arbitrary string by calling string copy multiple times by collecting the character by character from the existing string literals in the program. So you can basically write any kind of program using the ROP. And we also learned about like even the case that we do not have a pop RDI return, but in the most of the compilers it will generate like this kind of the code snippet. Then like we can reuse these as a gadget. Then we can set RDX by controlling all the other registers. It's a little complex, but if there's a possibility, then in computer science, the important thing is like, is it possible or not? So if it is possible, then we can let the computer do all the complex thing for us. Then like don't worry about the complexity. Then if there's a way, then hackers, we can write the code to get it done. And in week 6, we learned sequential read, arbitrary read, and arbitrary write as a new concept of the like basic attack primitives. And we turned the format string vulnerability into each of these primitive, either sequential read or arbitrary write. So this works as a sequential read, and this is for arbitrary write. So setting the address, getting the argument, and then writing the arbitrary value to the address. Yeah. And in week 7, we are introduced with more interesting challenges that requires playing the tricks with the systems. And I will do tutorials for some of the challenges of the week 7 today. So please come to the Zoom meeting at 3 p.m. Yeah. So in summary, using arbitrary read, sequential read, and arbitrary, so we can break ASLR by leaking some pointers because the relative offset within the certain memory region is fixed. And with the arbitrary read or sequential arbitrary write or sequential write, we can directly overwrite the return address, function pointers, and GOT entries that lead us to achieve the control flow hijacking. And overwriting the control data. Control data means return address, function pointers, and GOT entries that may change the control of the program, and the data that is used for changing the control flow. Yeah, and overriding control data means that we can change the control flow so that it's a control flow hijacking. And if we can do that and running binsh, that means like we can achieve arbitrary code execution. And if you search for the arbitrary code execution is something like some of the critical attack and the computer programs. Yeah. Then how can we defeat arbitrary code execution attack? So because this is a critical attack, as a security researcher, we need to think about how to defeat the thing. That's the topic for today. And for this, recall that our focus on week 6 was by using arbitrary write capabilities and use it in whatever method. Our goal is to overwrite the control data, such as a return address, GOT entries, and function pointers. Then an easy way to defeat such an attack is that do not let attacker overwrite those important control data. So return address, GOT entries, function pointers after we write the summary address legitimately and block the write permission, then we can protect the data. Yes, the words are cheap, but implementing that is difficult because we cannot set the memory permission in the byte or 4-byte granularity. So most of the memory permissions are done applied in the 4 kilobyte granularity. So we cannot implement such a write protected pointers or something like that. But we can change the program to act like that. So in this series of the slides, I will briefly go over some of the techniques that implements protecting the control data, such as shadow stack and control flow integrity and code pointer integrity. And also I will also introduce another way of defeating the arbitrary code execution attack by enhancing the ASLR further. So we will learn about what is the fine-grained code randomization and also a continuous code randomization. So let's get into these defenses. First is a shadow stack. So shadow stack is an easy concept for protecting the return address. Basically, it stores the return addresses separately. So what it means is that, so we know that the return addresses are important, and then it should not be changed after the function has invoked before the returning the function. So if we can let the attackers never overwrite the return address during that period, then the security is preserved. So the main question is that right now we have the return address in the same stack with the buffer. So if we overflow the buffer, we can overwrite the return address. Then why do we store the return address on the same stack with the buffer? So if we have a different stack for those control data at the start, then whatever we do for the overflowing the buffer, because that data will be on a different stack, then will never overflow to the return addresses at all. Then we can protect the return addresses. Yeah. So it does not require like that we put the return address and the buffer in the same stack, but the computers are designed in a naive way, so like there was no concept with security at the origin, so it just used one stack, but we can actually like having a separate stack for storing the return addresses because they are important. Yeah. So that concept is called the shadow stack. And so it's something like, suppose we have a function call like this, and we will store a return address here if we make a function call. And at the shadow stack, we can store the same value, the return address, at the function invocation. And then during the function execution, we will have the stack like this. And even if like some of the exploits overwrite all the things and then the return address points to the shellcode address, then when we return back to the original function, then what we will do is like we will compare the return address in the stack and in the shadow stack. If these values are equal, then it will return. Otherwise, it will raise an alarm that the detection of the buffer-overflow attack. Then we can defeat the return address overriding attack based on the buffer-overflow using shadow stack. So idea of having a shadow stack was proposed in early 1990s, right after the identification of the buffer-overflow vulnerability. However, changing how CPU manages call and return, because we need to like compare the data before returning the function, and also before calling the function, we need to store the return address to the shadow stack, and that affects a lot on the branch predictor, or also for the speculative execution behavior, which are critical to the processor's performance. So that means like the applying shadow stack affects on the performance of the program. So that's why it's not used in the reality. And so I would like to introduce one paper titled "The Performance Cost of the Shadow Stacks and the Stack Canaries." And this paper implements a very efficient shadow stack. And its scheme is something like whenever we have a function call, you can regard each colored region as a stack frame of one of the function, and then each function frame will have the return address, and this is the shadow stack, and then we will store the return address, the duplicated return address in here, and then if the buffer overflow happens in R3 maybe, and then if it overwrites the return address, then we can detect that because the value in the main stack differs from the shadow stack, then we will raise the alarm for that. And by using this kind of the simple scheme, like having a duplicate the shadow stack in a fixed location, fixed distance from the main stack, yeah. So the others had around the 3.5% of the performance cost in the average. So we can protect the return address from any kind of attacks. So think about it. Even if we overwrite the return addresses here, if we don't overwrite the return addresses in the shadow stack, then like the return target is invalid. So we cannot launch the control flow hijacking attack here. So by making the return addresses unchangeable, we can provide a fundamental defense against the return address overriding attacks. So this is easy. So for the return address protection, we can just apply the shadow stack. Then what about the other control data, such as function pointers or GOT entries? And the researchers attempt to generalize the return address protection using a shadow stack. The defense called control flow integrity. Yeah, that is the work. and it aims to provide a property that the attackers may not alter pointers that affects to the control flow of the program. So here's like the pointers that affects to the control flow of the program. This actually includes the return address and also function pointers, GOTNGs, any kind of the address that points to the function. Yeah. So this security mechanism, control flow integrity, would like to assert that property that like attackers can never alter those pointers, or like they can alter the pointers, but at least having the mechanism to check if the pointer is a legitimate call or return target or not. And then, like in control flow integrity, there are two types of the integrity. So for the and then these are backward edge and then forward edge. The reason why it's called the backward edge and forward edge. So think about like the making a function call from one of the function. So it's making a function call. It's a forward edge. So the sum of the function pointers, we use it by call instruction. That will be the forward edge control flow transition. And then when that function returns, that's the backward edge control flow transition. So it could be separated into the backward edge protection. So that's same as the return address protection. So you can regard the shadow stack and the stack address return address protection as a subset of the control flow integrity just for the backward edge. So you can regard this part and then we can rely this part on the shadow stack. And for the function pointers, we need a different approach. And for the forward edge protection, and that's called the forward edge protection. And we'll revisit what's the backward edge protection. Yeah. And one way to protect this is like the shadow stack, but there could be a different way to protect that. And let's take an example of this assembly code. So this function main, and in the main function, it will call the input function. And after calling input function, the program should return to the right next instruction. So we need to store this address, the instruction right next to the call instruction, as the return address. So for the return address, we need to store this address. Yeah. Then one of the property of the return address is that the return address should be some of the instruction address that is right next to the call instruction. Yeah. So if you return to some other instruction, pop return, pop return, or some other gadget that is not right next to the call instruction, that could be some of the illegitimate and not a legitimate return target. So we can define return target as any instruction right next to the call instruction. And by doing that, we can defeat some of the reusing of this kind of this kind of the wrap gadget, because if these are not right next to the call instruction, then we cannot one cannot use it for the return address target. Yeah. So by placing that kind of the simple property, we can defeat a lot of attacks. And another property could be, so when we are returning from the input function, so what we expect is that the return address should be the instruction right next to the call instruction, and the call instruction must be the address of the input function itself. So we can actually verify that too. So when we return from the input function, we need to go to the return address and check if the previous instruction is calling the function itself. Yeah. If that is not true, then we can reject the return. So we can restrict the number of the possible return targets, and there are many such of the defense. So one of the perfect defense could be like if we can collect all the legitimate control flow at the compilation time, yeah, and then apply that, or like applying the shadow stack, yeah. So that would be the better defense. But there could be some of the cases that we do not have the binary, the source code of the program. So in such a case, we need to apply the defense to the binary program directly. And in such a case, we have a limited view to the program. And one of the work called the control flow integrity for commercially off-the-shelf programs. Yeah, and this paper introduces how we can defeat the return-oriented programming attack in a binary program by using these two as security properties. So in summary, for backward edge protection, we can use a shadow stack, or we can apply these kind of the security property guarantee-based protection to the program. And for the forward edge protection of the control flow integrity, whenever we have an indirect call, for example, a call instruction to the register or some of the data values, such as a call EAX, and for these kind of for protecting this kind of the call transaction, we actually uses this kind of the instruction in the PLT GOT2. So when we call printf PLT, then it will do jump EAX. So we can regard that as a call EAX because there was a call to printf PLT. Yeah. So in that case, that will act as a indirect call, and for that kind of an indirect call, because we don't know whether this address is modified or not, so we need to verify that these addresses are valid or not. So we need to block the attacks such as the returning to arbitrary shellcode or rob gadgets, and also the return to arbitrary library functions, or the changing the function pointer to run the arbitrary code. Yeah. So for protecting the forward edge, the first category of protecting the forward edge of the control flow is called the control flow integrity. And what this mechanism is doing is that at the program's compilation time, the compiler collects all the legitimate call return targets by drawing this kind of the control flow graph. And after identifying all the legitimate control flow call return targets, and it will add the checks to every call and return to check if the current return address follows these predefined control flow graphs. Yes, it definitely requires some sort of analysis, but mostly it's done at the compilation time. So the slow analysis is okay because it's a one-time job. But the problematic thing is that on every call and return, we need to check if the current call target and also current return target is the valid and legitimate ones. Yeah. And to do that, the programs with the control flow integrity protection runs additional checks on every function call and return, and it has around 20% runtime performance over an average. So 20% is quite huge in some sense. And in another defense called the code pointer integrity is more like a shadow stack. So this control flow integrity is more like an analysis phase. So try to attempt to analyze the program and try to identify what are the legitimate control flow transition, and just allowing that. Yeah. But in code pointer integrity, it's more like a shadow stack kind of approach. So it's something like storing all the code pointers, including return address, function pointers, GOT entries, in a separate area, something like a shadow stack. Yeah. So it will define the safe region of the memory and separate all the code pointers into there. And no matter how attackers play with the data in the buffer, in the data region, yeah, they cannot reach to the secure memory. Yeah. And the mechanism defines such a secure memory by allocating the memory randomly, so making attackers never know about what is the address of the secure region. Yeah. So this would guarantee a stronger defense than control flow integrity. So in a similar analogy to with the shadow stack, we will have the full guarantee. But with some of the naive, some of the rule-based policy, the property-based rules, such as the return address must be the instruction address right next to the call instruction, and even for the call instruction itself, that should refer to the function that is returning right now. Yeah. So even with those kind of the properties, we could miss some of the cases, but the shadow stack is a perfect case. Likewise, control flow integrity, this one could miss some of the runtime variants in the legitimate control flow transition, but in the code pointer integrity, we don't need to care about that. So it will preserve the original value of the pointer, so it will guarantee the stronger defense. And the interesting point is that while the control flow integrity exhibits around the 20% overhead in performance in average, the code pointer integrity, the mechanism that provides a stronger guarantee, it incurs around 8% overhead in average. So it has a very better defense and then better performance. So CPI and the part of the CFI is applies to the Clang compiler. So if you are using a Clang compiler and compiling your code, you can apply some of the options such as F sanitize. Safe stack means like applying the shadow stack like feature in available from the Clang. And also if you apply CFI something, then it will apply the control flow integrity kind of protection to your binary program. And after having such defenses, the program will be harder to be exploited. So in summary, to defeat the control flow hijacking attacks, we can directly place protection or checking on control data. So for return address protection, we can apply shadow stack. And for forward edge protection, we can either apply control flow integrity or code pointer integrity. Then, does this mean the end of the hacking era? No, not at all. So for shadow stack and safe stack, so it requires some of the secure memory regions, and these secure memory regions are protected by the memory privilege level. So most of the implementation relies on having a fixed but randomly chosen memory allocation, and relying the security provide the fact that the attackers don't know where the such secure memory region is allocated. So same thing applies to the code pointer integrity. So all the mechanism that requires a safe region shares the same problem. So after having such defenses, researchers are coming up with the method to defeat such safe region hiding mechanisms. So for the interested students, please refer to these papers about like how they can defeat safe randomly allocated safe region and code pointer integrity. Yeah. And also the researchers are coming up with the other methods that are more powerful than return-oriented programming, which can bypass most CFI defenses called counterfeit object-oriented programming. So you can see in the paper, you can see the tables, something like this, and this row lists like the available defenses, and you can see a lot of X's about like all those defenses are not effective against this new attack. So new attack is keep developing. So this area is still in a cat and mouse game. So if there's a new defense, then there will be a new attack, and there will be a new defense, and so on. And then regarding the address space layout or randomization, so the current ASLR is coarse-grained. That means the ASLR is applied per module basis or per area basis. So it randomized each library file differently, and library code, heap, stack regions differently, but within the region, all the relative offset are fixed. So if you leak the address of the printf, then you can safely calculate the address of the system, because all the relative offsets are fixed. And so one leak will defeat the entire region, the ASLR. So like to defeat that kind of attacks, one of the solutions is that we can apply the finer grained ASLR in the granularity of the function or instructions. So one paper called the address space layout permutation. So in this work, when the system randomized the program's layout, in addition to randomize the area itself, it will also shuffle the orders of the function in the program. So for example, suppose you have 20 functions, then there are chances that the randomly shuffled 20 functions are like that we could have 20 factorial cases, and that will be around the 2 to the 61 cases of the randomization status. so making the attack significantly harder than the regular ASLR. So 32-bit ASLR, so we could have like around the 8-bit entropy, so 1 over like a 512 cases we could exploit the library's address space, but with this kind of the permutation, so we will definitely having more than 20 functions, maybe several thousands of the functions available in the libc, then like we could have the 1,000 factorial, then that means like it's kind of like the unattackable in a like the reasonable amount of the time, right? Yeah. And another work called the binary string. This work attempts to randomize the code instruction by instruction. So not just for the shuffling the function, it will shuffle the order of the instructions in a limited manner. So it's very hard to find the wrap gadgets with the single leak. So these defenses can make attack harder, but they cannot prevent the attack completely because suppose you have one format string vulnerability, and if you can make the format string attack to run the function that invokes the format string vulnerability again, then you could have an infinite loop for the arbitrary read. In that case, you can leak the binary content for multiple times. Then if you can leak the entire binary with this method, then no matter how you randomize the instruction by instruction or shuffle the function, if we have the entire binary and the addresses, then yeah, ASLR could be defeated. So the researchers are coming up with the more aggressive idea. So basically, that is even if we apply the fine-grained ASLR, so if attackers can launch arbitrary read or sequential read for multiple times, then the attack could be defeated. Then what about like a re-randomize all the addresses before attack happens? Then even if the attackers can collect the addresses with the arbitrary read or sequential read, then those data will not be valid, yeah, if we re-randomize the address. Yeah. So one work called the TASR, what it does is that the work is a timely re-randomization of the mitigating the memory disclosures. And then what it does is that, so if we have a write system call, then this is something data sending from the program to the attackers. So this may leak some of the address information. And then the read system call, this is something like we accept some of the input from the attackers. So that could be some of the exploit contains the address information. So if we leak some of the address via write, but before having the read system call after write, if we re-randomize the entire thing, yeah, then the attack addresses will be invalid in this read system call. So the idea is basically re-randomize the entire address if read was called after write. Yeah. So that will nullify the attack, but the problem is that it will incur around the 20% runtime overhead. Yeah. And then another work called the shuffler attempts to bind the re-randomizing trigger with the timing. Yeah. The method is that so think about the packet delay from the East Coast and the West Coast, and then suppose the attacker is coming from the online. Then the ping from the East to West is around 60 milliseconds or something. But if the system re-randomized all the addresses, suppose in every 50 milliseconds, then after they leak the address, after they get the address, before they get the address information, our system re-randomized all the addresses. Then after they compose the attack and get them back, then those addresses are all invalid. So we can actually defeat the attacks by this. So this paper shuffler dealing with the timing-based re-randomization, and further this work called the Morpheus further extended the shuffler to the hardware-enhanced version so that they can re-randomize the entire address in 5 microseconds or something, yeah, to protect the attack from the remote attackers. Yeah. And then if it is like a microsecond granularity, then it could defeat against local attackers too. So the same question again, is it the end of the era of hacking? No, we are not there yet. So I'm also keep doing research and developing efficient defense mechanisms because there's no single perfect efficient defense. And this is the table from one of our paper, and shows each of the defenses are good or not for the attacks that we define as a 1, 2, 3, 4. But you can see that all of the defense mechanisms are not good for the attack 4. Yeah. So still, there's no perfect defense. And this will be the still open problem, and then I bet this would be a long cat and mouse game. And this is the end of this course. So thank you for your attention and the hard effort on solving challenges. So please study hard for the learning new attacks and thinking about the defenses against them, and practice the security method and attack debugging analysis method that you learned from this class to your projects. And also, please fill the course evaluation from ESAT and as well as Ray, my professor. And for the final remark, we learned about the real hacking technique in this class. So please use your skills in a good way for fixing the vulnerabilities and demonstrating the attack could happen to urge that the vendors patch the vulnerability or something, but please do not use your skills in a bad way. So whenever you find the vulnerability in the real program, then what you can do is you can contact to the responsible vulnerability disclosure channel, such as if you found a vulnerability in a Microsoft project, then you can reach to the vendors, Microsoft directly, or if you found a vulnerability in an open source or some other program that participates the HackerOne, which is a vulnerability bug bounty program, then you can work with them. But I do not recommend you guys working with some of the gray market companies such as ZeroDeam, which allegedly buying exploits and then sell to the other nation state or something. So do not work with those companies. I highly recommend to take the responsible vulnerability disclosure channel with the vendors or official bug bounty channel. Yeah. And then some of these are some of the records that I, after I learned these kind of the skills and then participating in lots of the CTF challenges, and then I discovered some of the vulnerabilities in iPhone, and then by reporting that to the vendor Apple directly, I have assigned as the CVE ID, and also the Apple acknowledged the discovery. And after having such a discovery, you can do some of the presentations on the Black Hat, and then could be introduced in the TV news. And yeah, by doing this continuously, I also won the DEF CON CTF 2 times in 2015 and 2018. So all the contents that I prepared for this class is the real hacking techniques. So please keep working, and I hope you guys can also have fun with playing CTFs and solving the security challenges, hard security challenges every day, and learning from them. Yeah, and thank you for your attention, and let's meet at the tutorial at 3 p.m. and please have fun with the challenges for week 7.